Photometry. Photometry is the science of the measurement of light in terms of its perceived brightness to the human eye. It is distinct from radiometry, which is the science of measurement of radiant energy, including light, in terms of absolute power. In modern photometry, the radiant power at each wavelength is weighed by a luminosity function that models human brightness sensitivity. Photometry and the eye. The human eye is not equally sensitive to all wavelengths of visible light. Photometry attempts to account for this by weighing the measured power at each wavelength with a factor that represents how sensitive the eye is at that wavelength. The standardized model of the eye's response to light as a function of wavelength is given by the luminosity function. Photometric quantities. Measurement techniques vary depending on the effects under study and gave rise to different nomenclature. Use of the human eye as a detector led to photometric units weighed by the eye's response characteristic. Many different units of measure are used for photometric measurements. People sometimes ask why there need to be so many different units or ask for conversions between units that can be converted, lumens and candelas for example. We are familiar with the idea that the adjective heavy can refer to weight or density, which are fundamentally different things. Similarly, the adjective bright can refer to a light source which delivers a high luminous flux measured in lumens, or to a light source which concentrates the luminous flux it has into a very narrow beam, candelas, or to a light source that is seen against a dark background. Measuring light. In this video, we are going to see about measuring light. Use a reflected light meter to measure the light reflecting off your subject. The easiest way to ensure consistent results is to use a gray card. Position the gray card at the subject and make sure that it catches the light that will illuminate the subject. Stand at the camera position and take the reading of the gray card. If the scene contains a wide range of contrast between highlights and shadows, then the user may want to take a variety of readings by standing at the camera position and moving your gray card around the area to measure the light in the highlights as well as in the shadows. Determine the exposure based on the purpose of the shot. If the user wants to see into the shadows, then he needs to increase the exposure a bit. If he does not need to have the highlights overexposed, then he needs to reduce the exposure slightly. The user can also use a reflected light meter to read light emanating from a light source or passing through a translucent subject such as stained glass or liquid. There are various ways to use an incident meter. The easiest and most direct way is, with a hemisphere diffuser attached, stand at your subject and point the hemisphere toward the camera position. This works particularly well when shooting outdoors. The hemisphere approximates the three-dimensional shape of the human head and so takes into consideration the highlight and shadow areas of the subject. When working in daylight conditions, it is easiest set your meter to read in f-stops, but remember, the recommended aperture is based on an assumed normal exposure. Another way to use your incident light meter is, stand at your subject's position and shading the hemisphere or flat diffuser from other light sources, read each light source individually. This method works best when you want to exercise maximum control to achieve a very high level of consistency from shot to shot. In this scenario, I prefer to take my light measurements in foot candles rather than in f-stops. Advantages of incident meters. In this video, we are going to see about advantages of incident meters. A better alternative to reading the light in many scenes is to use an incident meter. Handheld incident meters read the intensity of light falling on the subject and are usually taken from the subject position. Because they are not affected by variances in subject color or reflectance, incident meters accurately record the amount of light falling on the subject. In the majority of situations, an incident reading is extremely accurate and records tones, colors, and values correctly. Advantages of reflected spot measurements. In this video, we are going to see about advantages of reflected spot measurements. Some reflected meters known as spot meters have the ability to take reflected readings of tiny areas of a subject from the camera position. Spot metering is an ideal solution in a lot of special situations where incident readings are impossible and normal reflected readings are unreliable. These include scenes with distant subjects, backlight, an extreme brightness range, highly reflective surfaces, or a main subject in motion. Spot metering. An 18% gray mid-tone area allows you to make an exposure that will record detail, tonality, and color accurately. Once you get accustomed to reading scenes, you will be able to tell which subject areas have an average reflectance, and even in the most contrasty situations, you will be able to take spot readings from critical areas. For example, by taking a spot reading of a tall green saguaro cactus, a medium-toned subject in the middle of a bright sandy desert, you will get an accurate reading of the important subject area. Spot meters also allow you to average readings from several brightness areas within a scene. In-camera spot meters versus handheld meters. Although a number of advanced SLRs offer spot metering capability, the metering angle is directly related to the focal length of the camera lens in use. Every time the lens is changed, the effective spot meter angle changes. With a normal lens in use, the spot metering angle may be 15 degrees or more. A handheld 1-degree spot meter, on the other hand, allows the most selective measurement of distant subjects and small areas in complex scenes. Color temperature. In this video, we are going to see about color temperature. Color temperature describes the specific color of a light, but instead of just simply referring to a light as green, red, or white, we talk about the color of a light in terms of Kelvin. This is a measurement of temperature, and a Kelvin measurement connected to a light source allows anyone to understand exactly the type of light which will be emitted from it. Kelvin itself is a measurement of temperature created in the 1800s by a British physicist called William Kelvin. Kelvin noticed that when heating up a block of carbon, that it changed color depending on the heat produced. This went from a low red color through yellow and blue before reaching a blinding white. This color profile is the reason why Kelvin is used to describe the type of light being produced. Working of color temperature. In this video, we are going to see about working of color temperature. It is quite simple to understand color temperature, sometimes referred to as correlated color temperature or CCT for short. So, don't be put off by the numbers attached. As we said previously, the color temperature of a light is measured in Kelvin. This normally ranges from around 2000 Kelvin to 7000 Kelvin for lights, but can go up to anywhere as high as 10,000 Kelvin. The higher the number, the closer the color produced is to pure white. This is similar to how a tungsten filament glows in a standard incandescent bulb. The more electricity passed through it, which increases the temperature, the whiter the light emitted. The lower amount of electricity used, and therefore the colder the filament, the closer to red the light becomes. This is why dimmer switches produce an almost red glow when used at their lowest settings. There is one issue which tends to confuse matters a little. Although the lower the temperature, the redder the color profile becomes, people still often refer to a light like this as being warm. Likewise, a bright white light which corresponds to a higher temperature is often described as a cold light. The reason for this disparity between the description and the actual Kelvin measurement is that warm is used to describe cozier colors such as red and yellow in relation to a fireplace, while whiter lights are seen as cold by being the polar opposite. Therefore, higher color temperatures are described as cold or cooler, while lower temperatures are described as being warmer. Common color temperature used includes 2700 Kelvin. This produces a warm, cozy light. It is similar to the yellow or white light produced by a standard incandescent bulb or candle. 3000 Kelvin. At this color temperature, the light becomes more white than yellow. This is similar to the light produced by an average halogen bulb. 3500 Kelvin. Fluorescent tubes tend to produce this type of light. It is again even whiter and can have very slight hint of blue to it. 4000 Kelvin. Again, fluorescence can be found with this color profile. This is even whiter still with more blue through the light. 6000 Kelvin. This is a close approximation of normal daylight. Fluorescent tubes produce this light, as can some LEDs. SAD, seasonal affective disorder, lights are also designed to produce light at this color temperature. 6500 Kelvin. A color profile often used to simulate other types of daylight with an exceptionally bright white. There are just some of the more common color profiles in use. However, many color profiles do exist. Using color temperature effectively. There are a number of ways to use color temperature when choosing a light. It all depends on the context and the purpose. Cold lights. A CCT of 5000 Kelvin to 6000 Kelvin is perfect for environments where high visibility is required. This bright white light is perfect for dentists' or doctors' offices where it is important to see every detail on close inspection. It is also perfect for a security light outside of a property, as it will intimidate any burglars or trespassers. Incandescent warm lights. These lights are perfect for relaxation. A cold light can feel sterile and too close to daylight, but a warm light around 2700 Kelvin promotes relaxation by simulating sunset light conditions. Great for areas where you want to entertain guests, eat food, or just want to relax with a book or in front of a television. Mid-range. Around 3500 Kelvin gives a good balance between both ends of the color temperature spectrum. It illuminates study areas brilliantly, but not with such a harsh light that it will cause eye strain of any kind. This is a great trade-off between visibility and appearance. Fantastic when used as a spotlight for a bookcase, painting, or object you wish to draw attention to. There are so many different color profiles available that the choice can be quite intimidating. Hopefully, with the above information now at hand, you will be able to look for a light color for your needs without fearing the jargon or terminology. Reflectance. In this video, we are going to see about reflectance. Reflectance photometry is the science of measuring the reflectance by a surface as a function of wavelength of light. white light is incident on a surface and the light reflected from the surface is then measured after passing through a monochromator. Measurement through reflectance photometry has mainly practical applications. Example, in the paint industry to characterize the color of a surface. List of reflectance for various materials. New asphalt 0.04 to 0.05. Black acrylic paint 0.05. Aged asphalt 0.1 to 0.12. Conifer forest 0.08 to 0.15. Bare soil 0.17. Deciduous trees 0.15 to 0.18. White asphalt shingle 0.2. Green grass 0.25. Aged concrete 0.2 to 0.3. Desert sand 0.4. New concrete traditional 0.4 to 0.55. Ocean ice 0.5 to 0.7. New concrete with white Portland cement 0.7 to 0.8. White acrylic paint 0.8. Fresh snow 0.8 to 0.9. Water 0.03 to 1.0. Old or melting snow 0.40 to 0.80. Tundra 0.2. Foot candles. In this video, we are going to see about foot candles. A foot candle is a non-SI unit of illuminance or light intensity widely used citation needed in the United States in photography, film, television, conservation lighting, greenhouse horticulture, the lighting industry, construction-related engineering, and in building codes. The name foot candle conveys the illuminance cast on a surface by one candela source 1 foot away. As natural as this sounds, this style of name is now frowned upon because dimensionally illuminance is not length times luminous intensity as the name would imply, but instead luminous intensity per unit area. The unit is defined as the amount of illumination the inside surface of a 1 foot radius sphere would be receiving if there were a uniform point source of one candela in the exact center of the sphere. Alternatively, it can be defined as the illuminance on a 1 square foot surface of which there is a uniform distributed flux of 1 lumen. Thus, 1 foot candle is equal to 1 lumen per square foot or approximately 10.764 lux. In practical applications, as when measuring room illumination, it is very difficult to measure luminance more accurately than plus or minus 10%, and for many purposes, it is quite sufficient to think of 1 foot candle as about 10 lux, as is typically done in the lighting industry. Brightness. In this video, we are going to see about brightness. Brightness is an attribute of visual perception in which a source appears to be radiating or reflecting light. In other words, brightness is the perception elicited by the luminance of a visual target. This is a subjective attribute or property of an object being observed. The adjective bright derives from an Old English "bright" with the same meaning via metathesis, giving Middle English bright. Brightness was formerly used as a synonym for the photometric term luminance and incorrectly for the radiometric term radiance. As defined by the U.S. Federal Glossary of Telecommunication Terms, FS 1037C, brightness should now be used only for non-quantitative references to physiological sensations and perceptions of light. A given target luminance can elicit different perceptions of brightness in different contexts. See, for example, White's illusion. In the RGB color space, brightness can be thought of as the arithmetic mean mu of the red, green, and blue color coordinates. Mu is equal to R plus G plus B divided by over 3. Brightness is also a color coordinate in the HSB or HSV color space, that is hue, saturation, and brightness or value. With regard to stars, brightness is quantified as apparent magnitude and absolute magnitude. Contrast ratios. In this video, we are going to see about contrast ratios. The contrast ratio is a property of a display system defined as the ratio of luminance of the brightest color, that is white, to that of the darkest color, that is black, that the system is capable of producing. A high contrast ratio is a desired aspect of any display. It has similarities with dynamic range. There is no official standardized way to measure contrast ratio for a system or its parts, nor is there a standard for defining contrast ratio that is accepted by any standards organization. So, ratings provided by different manufacturers of display devices are not necessarily comparable to each other due to differences in method of measurement, operation, and unstated variables. Manufacturers have traditionally favored measurement methods that isolate the device from the system, whereas other designers have more often taken the effect of the room into account. An ideal room would absorb all the light reflecting from a projection screen or emitted by a CRT, and the only light screen in the room would come from the display device. With such a room, the contrast ratio of the image would be the same as the contrast ratio of the device. Real rooms reflect some of the light back to the displayed image, lowering the contrast ratio seen in the image. Static contrast ratio is the luminosity ratio comparing the brightest and darkest color the system is capable of producing simultaneously at any instant of time, while dynamic contrast ratio is the luminosity ratio comparing the brightest and darkest color the system is capable of producing over time while the picture is moving. Moving from a system that displays a static motionless image to a system that displays a dynamic changing picture slightly complicates the definition of the contrast ratio due to the need to take into account the extra temporal dimension to the measuring process. Reciprocity law. In this video, we are going to see about reciprocity law. In photography, reciprocity is the inverse relationship between the intensity and duration of light that determines the reaction of light-sensitive material. With a normal exposure range for film stock, for example, the reciprocity law states that the film response will be determined by the total exposure, defined as intensity x time. Therefore, the same response, for example the optical density of the developed film, can result from reducing duration and increasing light intensity and vice versa. The reciprocal relationship is assumed in most sensitometry, for example when measuring a Herter and Rietveld curve optical density versus logarithm of total exposure for a photographic emulsion. Total exposure of the film or sensor, the product of focal plane illuminance times exposure time, is measured in lux seconds. Reciprocity law failure. In this video, we are going to see about reciprocity law failure. For more photographic materials, reciprocity is valid with good accuracy over a range of values of exposure duration, but becomes increasingly inaccurate as we depart from this range. This is reciprocity failure, reciprocity law failure, or the Schwarzschild effect. As the light level decreases out of the reciprocity range, the increase in duration and hence of total exposure required to produce an equivalent response becomes higher than the formula states. For instance, at half of the light required for a normal exposure, the duration must be more than doubled for the same result. Multipliers used to correct for this effect are called reciprocity factors. At very low light levels, film is less responsive. Light can be considered to be a stream of discrete photons, and a light-sensitive emulsion is composed of discrete light-sensitive grains, usually silver halide crystals. Each grain must absorb a certain number of photons in order for the light-driven reaction to occur and the latent image to form. In particular, if the surface of the silver halide crystal has a cluster of approximately 4 or more reduced silver atoms, resulting from absorption of a sufficient number of photons, usually a few dozen photons are required, it is rendered developable. At low light levels, that is few photons per unit time, photons impinge upon each grain relatively infrequently. If the 4 photons required arrive over a long enough interval, the partial chain due to the first 1 or 2 is not stable enough to survive before enough photons arrive to make a permanent latent image center. This breakdown in the usual trade-off between aperture and shutter speed is known as reciprocity failure. Each different film type has a different response at low light levels. Some films are very susceptible to reciprocity failure and others much less so. Some films that are very light sensitive at normal illumination levels and normal exposure times lose much of their sensitivity at low light levels, becoming effectively slow films for long exposures. Conversely, some films that are slow under normal exposure duration retain their light sensitivity better at low light levels. For example, for a given film, if a light meter indicates a required EV of 5 and the photographer sets the aperture to f/11, then ordinarily a 4-second exposure would be required. A reciprocity correction factor of 1.5 would require the exposure to be extended to 6 seconds for the same result. Reciprocity failure generally becomes significant at exposures of longer than about 1 second for film and about 30 seconds for paper. The reciprocity also breaks down at extremely high levels of illumination with very short exposures. This is a concern for scientific and technical photography, but rarely to general photographers, as exposures significantly shorter than a millisecond are only required for subjects such as explosions and particle physics experiments, or when taking high-speed motion pictures with very high shutter speeds, 1/10,000 seconds or faster. Exposure controls. In this video, we are going to see about exposure controls. A photograph's exposure determines how dark or light an image will appear when it is being captured by your camera. Believe it or not, this is determined by just 3 camera settings: aperture, ISO, and shutter speed, the exposure triangle. Understanding exposure. Achieving the correct exposure is a lot like collecting rain in a bucket. While the rate of rainfall is uncontrollable, 3 factors remain under your control: the bucket's width, the duration you leave it in the rain, the quantity of rain you want to collect. You just need to ensure you don't collect too little underexposed, but that you also don't collect too much overexposed. In photography, the exposure settings of aperture, shutter speed, and ISO speed are analogous to the width, time, and quantity discussed above. The differences in exposure control in camera. Exposure triangle. In this video, we are going to see about exposure triangle. The exposure triangle is a catchy phrase meant to encompass the 3 factors which affect the exposure of a photograph of a scene with a given amount of light. The exposure triangle is an aid to remembering the 3 controls and helping photographers to think through the process of setting each of them to achieve the exposure required. Each setting controls exposure differently. Aperture controls the area over which light can enter your camera. Shutter speed controls the duration of the exposure. ISO speed controls the sensitivity of your camera's sensor to a given amount of light. One can therefore use many combinations of the above three settings to achieve the same exposure. The key, however, is knowing which trade-offs to make, since each setting also influences other image properties. For example, aperture affects depth of field, shutter speed affects motion blur, and ISO speed affects image noise. Shutter speed. In this video, we are going to see about shutter speed. Shutter speed is the length of time a camera shutter is open when taking a photograph. In film photography, it was the length of time that the film was exposed to the scene you are photographing, and similarly in digital photography, shutter speed is the length of time that your image sensor sees the scene you are attempting to capture. Higher shutter speed, 30+ seconds, specialty night and low light photos. The waterfall picture is with slower shutter speed, ½ second. It is to have a silky look to flowing water. Landscape photos on a tripod for enhanced depth of field. 1:2 to 1:30 second. To add motion blur to the background of a moving object, carefully taken handheld photos with stabilization. 1:50 to 1/100 second. Typical handheld photos without substantial zoom. 1:250 to 1/500 second. To freeze everyday sports or action subject movement, handheld photos with substantial zoom, telephoto lens. 1/1000 to 1/4000 second. To freeze extremely fast, up-close subject motion. Aperture setting. In this video, we are going to see about aperture setting. A camera's aperture setting controls the area over which light can pass through your camera lens. It is specified in terms of an f-stop value, which can at times be counterintuitive because the area of the opening increases as the f-stop decreases. In photographer slang, when someone says they are stopping down or opening up their lens, they are referring to increasing and decreasing the f-stop value respectively. By the numbers, every time the f-stop value halves, the light collecting area quadruples. There is a formula for this, but most photographers just memorize the f-stop numbers that correspond to each doubling or halving of light. ISO speed. In this video, we are going to see about ISO speed. The ISO speed determines how sensitive the camera is to incoming light. However, unlike aperture and shutter speed, a lower ISO speed is almost always desirable since higher ISO speeds dramatically increase image noise. As a result, ISO speed is usually only increased from its minimum value if the desired aperture and shutter speed are not otherwise obtainable. Common ISO speeds include 100, 200, 400, and 800, although many cameras also permit lower or higher values. With compact cameras, an ISO speed in the range of 50 to 200 generally produces acceptably low image noise, whereas with digital SLR cameras, a range of 50 to 800 or higher is often acceptable. Hollywood lighting. In this video, we are going to see about Hollywood lighting. Lighting performs essential functions in Hollywood films, enhancing the glamour, clarifying the action, and intensifying the mood. Closely analyzing Girl Shy 1924, Anna Karenina 1935, Only Angels Have Wings, 1939, and Teen Men, 1947, along with other brilliant classics. Keating describes the unique problem posed by these films and the innovative ways cinematographers handle the challenge. Once dismissed as crank-turning laborers, these early cinematographers became skillful professional artists by carefully balancing the competing demands of story, studio, and star. Cinematographers were masters of multifunctionality and negotiation, honing their craft to achieve not only realistic fantasy but also pictorial artistry. Expressionist lighting. In this video, we are going to see about expressionist lighting. Expressionist lighting is a way of experimenting with lighting to illustrate different emotions and moods in the photograph. Use expressionistic lighting in artistic photography with information from a professional art and commercial photographer in this free video on photography. Films such as the original Lon Chaney film Phantom of the Opera, which can be viewed here, and Bela Lugosi in Dracula were two horror films that were greatly influenced by the genre. Films such as Dark City, Psycho, many monster and horror films as well as film noir were also influenced by the expressionist use of light and shadow to create emotion or action. Directors such as Billy Wilder, Otto Preminger, Alfred Hitchcock, and Michael Curtis, and even the contemporary Tim Burton all have styles of filmmaking that can be easily traced back to the roots of German Expressionism. The artistry and creativity of this unique genre of film shows us that you don't need special effects or even color and sound to create a film that is as spine-tinglingly frightening or emotionally thoughtful as the film we have today. Expressionistic lighting is when you want to experiment with your lights a little bit more. There is no set in stone rules on how you do it or where the lights go. It's pretty much whatever you want to do. The important thing here is to show different emotions. If you are photographing, for example, a dream sequence, you might only have one harsh light coming from below to have a scary sort of look, or perhaps you might put the light behind the person just to get a silhouette of them, and with this, it's pretty much whatever your imagination says, that's what you can try. Experimenting with the lights and discovering what it is that you want to happen with the lights when you are using expressionistic lighting. Neo-realist lighting. In this video, we are going to see about neo-realist lighting. The cinematography in this film was the example of the moment. The use of simplistic angles is apparent. This film, shot in black and white, possesses many two shots in place of alternating perspectives during a conversation. Also, the film contained many eye-line matches. This added to the film continuity. The lighting also was characteristic of the moment. Ambient lighting is used in many of the scenes. This gives a footage a more realistic appearance. This film utilizes the camera and lighting to create many moods and emotions. The use of natural lighting in this film follows the moment. This use of natural lighting gives many scenes a rough appearance. The use of long shots is also apparent. This builds focus on the acting and on the location of filming. Cinematography is used to help present the struggle faced by the main character. The film utilized natural lighting. The use of long shots allowed for emphasis on actor's emotion and the location of the filming. The emphasis on location is a characteristic of this moment. Softening of images. In this video, we are going to see about softening of images. Lighting does more than just expose the image. It's one of the very basic tools that filmmakers have at their disposal to create an atmosphere for their story. In Hollywood films, there are various uses of hard lights and soft lights, but most often hard lights are used to fake daylight since the sun itself is a hard source. What is soft light? On camera, frontal light is very even to a fault. It comes from the same angle that the lens sees, so there are no shadows on the subject. The top picture is direct flash and is a small light, but it is off camera so that its shadow will still show shape of the subject. Hard light from the small direct flash about where the top of the umbrella would be same angle causes dark, sharp shadows, which is more contrasty. Certainly, it is not flat lighting and not real dark here because the white background curved up just a few inches away is a reflector providing some fill. Shadow is darker at front than at rear. Hard side light emphasizes details of texture. For example, the egg texture where the light is at 90 degrees to the surface, or for example, similar low side direct lighting is great to photograph the detail in a coin. It makes dark surface shadows to show contours, but showing all surface detail is not always a plus. In skin complexions or wrinkles, for example, and soft light has no dark shadows to emphasize surface texture. What is soft light? It is large, white light that diffuses the shadows, converting them to subtle gradient tones that wrap around the subject. Lighting is all about the smooth tonal gradients, which we call soft, obviously softer than harsh, hard, dark shadows. Tonal variation. In this video, we are going to see about tonal variation. In photography, the tonal range or tonality is mainly an expression of contrast. A long range referred to as high contrast, a medium range means moderate contrast, while a short range refers to low contrast or flatness. The term tone refers to any area of uniform density on a print, negative, transparency, or pixels on a screen. A rich range of tones in a colored as well as a black and white image is vital to its success. In digital photography, this is limited to the sensor's dynamic range and its ability to capture a wide enough distribution of tones that would be considered suitable for the purpose of the photo. Factors that influence tonal range of the final image include subject reflectance as well as the lighting. A high reflectance subject accompanied by highlighting results in a long span of image tones that are probably beyond any sensor's capabilities. Light size and quality, harsh or soft, also control the tonal range of a scene. So, do special effect filters such as polarizing filters that are known to increase color vibrancy and expand tonal range. Diffusers and similar light control equipment lessen contrast, thus reducing the tonal range. The bit depth used to encode an image has an effect on the tonal range of that image. 8 bits yield 256 discrete levels of information, which is the minimum number of levels that produces visually continuous tones, while 16 bits yield 65,536 discrete levels of information. Famous American landscape photographer Ansel Adams devised what is known as the zone system. The zone system can be applied for obtaining correct exposures under different circumstances, no matter how tricky. Good knowledge of the zone system as well as a solid experience in applying it allow user to accurately tune the result up or down the tone scale and to successfully contract or expand the range it occupies on that scale for technical or creative purposes. Tonal range. In this video, we are going to see about tonal range. In photography, tonal range refers to mid-tone values expanding to occupy the scale between the lightest and darkest points of an image. The wider the range expands, the more contrast there is, and the more mid-tone values would be represented in the image. An image with a narrow tonal range would cover a more restricted area between its lightest and darkest values, thus mainly consisting of mid-tones and in turn having less contrast. The histogram gives us a really good idea about the tonal range of an image on a scale of 0 to 255. The white point, the point on the rightmost side of the scale, has a value of 255 and is purely white. And the black point, the point on the leftmost hand side of the scale, has a value of 0 and is purely black, as well as a number of points between pure black and pure white that constitute the midtones. If, however, there were blank areas between successive midtone values on a histogram, this would yield a visible stepping of shades in a gradient constituting graduated colors that break into larger blocks of a single color, reducing the smooth look of a proper gradation. Incandescent lamps. In this video, we are going to see about incandescent lamps. Incandescent light is produced in a bulb containing a filament, usually tungsten, and will produce a warmer, redder color than sunlight. Design and operation. Light in an incandescent lamp is produced by a tungsten filament heated by electric current. The red-hot tungsten filament, about 2800 Kelvin, is in a bulb filled with a noble gas. The electric connection is made possible by a special base at one or both ends. Technical data. The rated voltage of incandescent lamps mainly used for lighting interiors is 220 to 230 volt. Low voltage 6, 12 and 24 volt lamps are mainly used for safety reasons. The values of rated wattage of normal incandescent lamps are 25, 40, 60, 75, 100, 150, 200, 500, 1500 and 2000 watts. Different bases are used for different rated inputs of lamps as follows. E14 base is used for 25 to 40 watts. E27 base is used for 25 to 100 watts. E40 base is used for 150 to 2000 watts. Cost efficiency. The luminous efficiency of incandescent lamps is 6 to 20 lumens per watts. Their lifetime is usually 1000 hours, but it may be more than double in certain types. Their initial cost is generally low due to their simple design. Their initial cost per produced luminous flux is the lowest, although the price ratio of certain types may be 1:8. Operating qualities. Incandescent lamps produce total light practically immediately after they have been switched on. Starting time is less than 0.1 second. They provide total luminous flux without delay when they are switched on immediately after being switched off or following a break in the voltage of the network. Restarting time is less than 0.1 second. Their life is affected by the voltage of the voltage supply. The larger the voltage, the shorter the lamp's lifetime. The operating temperatures of the bulb and the base are high. Temperatures at the top of the bulb may exceed 300 degrees Celsius. Temperatures along the lamps depend on the burning position. Their burning position is optional. Tungsten halogen lamps for main voltage. In this video, we are going to see about tungsten halogen lamps for main voltage. The tungsten halogen lamp design differs from that of standard incandescent lamps in the following ways. The light source is linear, the envelope is made from quartz glass, and the tube contains halogens, hence the name. Bases are situated at both the ends of the tube. Their operation is the same as that of standard incandescent lamps. The quality of light. The spectral distribution of their light is practically the same as that of standard incandescent lamps. Their color temperature is low, 2800 to 3300 Kelvin, so the color of their light is warm. Their color rendering is excellent, RA is equal to 1A. Technical data. Their rated voltage is generally between 220 to 230 volts. Their rated wattages are 100, 150, 200, 250, 300, 500, 750, 1000, 1500 and 2000 watts. They have special bases for electric connection. The luminous flux generated by one lamp is 1300 to 44,000 lumens. Cost efficiency. The luminous efficacy of these halogen lamps is 13 to 22 lumens per watt, better than that of standard incandescent lamps. Their lifetime, 2000 to 3000 hours, is longer than the lifetime of standard incandescent lamps. Their initial cost is generally low due to their simple design. Their initial cost per produced luminous flux is somewhat by about 25% higher than that of the cheapest standard incandescent lamps. Operating qualities. Halogen lamps produce total light practically immediately after they are switched on. Starting time is less than 0.1 second. The operating temperature of the bulb may exceed 300 degrees Celsius. They provide total luminous flux without delay when they are switched on immediately after being switched off or following a break in the voltage of the network. Restarting time is less than 0.1 second. Their burning position is horizontal, 4 to 15 degree. Fluorescent lamps. In this video, we are going to see about fluorescent lamps. Fluorescent light, a common form of illumination in offices, has a more complicated light emission mechanism than incandescent light. Ultraviolet rays created within fluorescent lamps are transferred into visible light that we can see. Design and operation. The light is produced predominantly by the fluorescent powder covering the inner wall of the tube. The powder transforms the UV radiation of the gas discharge into visible light. Fluorescent lamps can only operate with the help of auxiliaries, starter, ballast, capacitor, electronic control gear, etc. Fluorescent lamps convert about 1/4 of their input into light. This ratio is smaller if the auxiliaries are also taken into account. The quality of light. The quality of light of fluorescent lamps may vary depending on the composition and quality of the fluorescent powder. Consequently, the spectral distribution of their light may also vary. Their color temperature may be 2900 to 6500 Kelvin, so their light may be warm, neutral, or cool. Their color rendering varies too. RA is equal to 1A, 1B, 2A, 2B, or 3. Technical data. The rated voltages of the tubes are between 57 and 110 volt, which means that they can be operated from the 230 volt of the network if the proper auxiliaries are used. Depending on the sort of the ballast, the input from the network exceeds that of the lamp by about 20% in case of normal ballast, 10% in case of low loss ballast, 5% in case of electronic ballast. The luminous flux generated by one lamp is 1000 to 5400 lumens. Cost efficiency. The luminous efficacy of fluorescent lamps depends on the fluorescent powder used, the rated wattage, the diameter. Depending on the above parameters, their luminar efficacies are 50 to 75 lumens per watt for dia 38 mm, 70 to 95 lumens per watt for dia 26 mm, 95 to 105 lumens per watt for dia 16 mm. Mercury lamps. In this video, we are going to see about mercury lamps. Mercury vapor lamp means a high-intensity discharge lamp including clear, phosphor-coated and self-ballasted screw-based lamps in which the major portion of the light is produced by radiation from mercury, typically operating at a partial vapor pressure in excess of 100,000 Pascal, approximately 1 atmospheric pressure. Design and operation. Mercury lamps belongs to the group of HID, that is, high-intensity discharge lamps. These lamps have two envelopes. The inner quartz envelope is an arc tube. The gas discharge is started by a starting electrode. The radiation generated by the electric current through mercury vapor is only partly light. Its invisible part is transformed into light by the fluorescent powder on the inside surface of the outer envelope. Mercury lamps need auxiliaries, ballast or starter transformer for their operation. Mercury lamps convert only about 1/6 of the input into light. This ratio is smaller if the consumption of the auxiliary is taken into account. The quality of light. The quality of their light may vary depending on the fluorescent powder used. Their color temperature is 3350 to 4000 Kelvin, so their light is warm or neutral. Their color rendering is bad, Ra is equal to 3, their luminance is high. Technical data. Their rated lamp voltage is 95 to 145 volts. Their rated lamp wattages are 50, 80, 125, 175, 250, 400, 700 and 1000 watts. Cost efficiency. The luminous efficacy of the lamps is 30 to 60 lumens per watt, but these values are smaller if the auxiliary is taken into account. The lifetime of mercury lamps is 8,000 to 20,000 hours. Operating qualities. Mercury lamps produce total luminous flux in a matter of minutes after they have been switched on. Starting time is 2 to 5 minutes. Total luminous flux is produced in about 10 minutes after they have been switched off and on. Restarting time is 10 minutes. Metal halide lamps. In this video, we are going to see about metal halide lamps. It is a powerful source of light. This type of lamp is known as MH lamp. It is an HID lamp, that is high intensity discharge, which means it provides most of its lights from the electric arc within a small discharge tube. It is becoming increasingly popular due to its good quality white light and good efficiency. The most prominent use of the MH lamp is in stadiums and sports fields. It is also used widely for parking lots and street lighting in urban areas. Design and operation. Metal halide lamps are HID lamps too. They have two envelopes. The inner quartz arc tube contains other metal halides in addition to mercury. Light is generated in the arc tube either with the help of an auxiliary electrode or with the help of a starting impulse. The outer envelope may or may not have a fluorescent powder coating. Metal halide lamps convert only about 1/4 of the input into light. This ratio is smaller if the consumption of the auxiliary is taken into account. The quality of light. Their quality of light depends on the metal halides used in the arc tube. Their color temperature is 3000 to 6000 Kelvin, so their light may be warm, neutral or cool. Their color rendering is usually good. Ra is equal to 1A, 1B or 2A. Cost efficiency. The luminous efficacy of the lamps is 55 to 110 lumens per watts. These values are smaller if the auxiliary is taken into account. The lifetime of metal halide lamps is 2000 to 10,000 hours. Operating qualities. Metal halide lamps produce total luminous flux in a matter of minutes after switching on. Starting time is about 5 minutes. Total luminous flux is produced in about 10 minutes after they are switched off, and on restarting time is 10 minutes. In some special types with extra built-in electrodes, restarting time is only a few seconds. Zooming. In this video, we are going to see about zooming. An LED has a beam angle of 120 to 180 degrees. The hot spot that can be observed with most reflector type lights are the result of the outside of the LED beam pattern that is folded and directed by the reflector. There are some losses due to the imperfect reflection surface of the reflector, but it is minimal. In this example, the red part is folded and redirected forward, where the middle section leaves the light unaffected. The shape of the reflector is very important. There are two ways to increase the hot spot of the reflector type light. The first is to make the reflector deeper, and the second is to make the reflector wider. In both the cases, more of the light emitted by the LED is folded and directed forward. The advantages of reflector type lights are that they make use of more of the available light, as well as having a combination beam with both flat and focused areas. Zoom lens lights. Depending on the design, the lens or the LED position can be adjusted to change the distance between the two. As the distance changes, a different part of the beam emitted by the LED is captured and deflected. The picture defines the light in focused mode and flood mode. Focused or zoomed mode. When the distance is the greatest, the lens catches only the light that is traveling directly at the lens. When the light enters the lens, its angle is changed and then travels in a focused beam. As can be seen, most of the light is wasted when the light is in this mode, although the beam is more concentrated to some extent. If it is assumed that the amount of light is uniform over the LED beam angle, which to some extent it is, then a significant amount of light is on the outside of the beam. Just to illustrate, we made a quick calculation based on area, and in this example, 86% of the light emitted would be wasted. This should, in reality, not be as dramatic because the spatial distribution is not uniform. It does show that a significant amount of light is wasted in zoomed mode. Spotlight. In this video, we are going to see about spotlight. A spotlight is a general term for any lighting instrument used in theater to create a pool of light on the stage. There are many different types of spotlights which break down into three general areas: Fresnel lanterns or Fresnels US, profile spots UK, ellipsoidal reflector spotlight. Fresnel lanterns or Fresnels US. A Fresnel lantern US, or simply Fresnel US, employs a Fresnel lens to wash light over an area of the stage. Fresnel lanterns or Fresnels US are small fixtures giving a soft-edged spot or pool of light. Their name comes from the distinctive ridged Fresnel lens used on the front. The resulting beam of light is wide and soft-edged, creating soft shadows, and is commonly used for backlight, top light, and side light. Fresnels use a spherical reflector with a lamp at the focus point. The lamp and reflector remain a fixed unit inside the housing and are moved forward and back to focus the light. Profile spots UK. Profile spots UK tend to be longer fixtures containing convex lenses and having a gate at their focal point, which enables the insertion of gobas or irises to shape the beam of light. They give a hard-edged beam, most often associated in the public mind with spotlights. Ellipsoidal reflector spotlight. The ellipsoidal reflector spotlight, that is ERS, also known as profile, after its ability to project the silhouette or profile of anything put in the gate, UK, and decoupe, French, is the most abundant instrument type currently used in theoretical use. The flexibility of the ERS allows it to fulfill the bulk of lighting roles in the theater. The major components of an ERS light are the casing in which the internal parts are mounted, an ellipsoidal reflector located in the back of the casing, a lamp mounted to position the filament at the rear focal point of the ellipsoid, a dual plano-convex lens, two plano-convex lenses facing each other in the barrel, and at the front a gel frame to hold the color gel. The light from the lamp is efficiently gathered by the ellipsoidal reflector and sent forward through the gate, shutters, and lens system.